Okay, new model. We're gonna make Dimitri's thing. So now we need multiple physics. We need the electric fields and currents that we dearly love, but we also need electric currents in shells. We need both of them for this. So we're going to add the electric currents first, then we'll add electric currents in shells. Once again, we're just going to do stationary, and we are going to go. Work plane. $70 microns. That is thin. To call you sample.
Hey, sorry, the landlord guy wants things.
Can we do that? Okay, sounds good. So Up, down, left, right. So now we're going to explain how to add a conducting or insulating surface. This is Dimitri's last sample. So we're going to do the standard thing where we define the resistivity and the Hall resistivity. But in addition to that, we are going to also define the sheet bulk and the sheet longitudinal and the sheet Hall. Gotta give these numbers or else they don't stay. So now in the Materials tab, what we are going to do is we are going to define a layered material. We only need one layer, so we can do this and it's fine. Single layered material. We're going to call this the surface. And it is going to have U. Love it, love it, love it. So we're going to give it a relative permittivity of 1, and the electrical conductivity, we're just going to set it as 1 for now. We'll get back to that later. So okay, so now that we have the surface, boop, with our 1s, what we are going to do is we are going to go to electric currents in shells. And it'll have a bunch of stuff set by default. The first thing we need to do is we need to go to non-layered shell, and we need to change that to layered shell. And then we need to restrict to a layered boundary. Remember that a moment ago we set the bulk boundary to be a layered boundary. So what we do in here is only going to affect the bulk of the sample. The equations and stuff that we have, we don't really have to worry about it too much, because all the fun stuff is going to happen in the material. So back in the material, this is the layered material that we have. We're going to give it a thickness that is a very small thickness. Let's say 1 to the 9, 1 nanometer thick. We'll keep everything else for now. And this sample, it has its bulk overridden. Cut. Resume. So now that we have the resistivities defined, we are going to go to the materials, and in the sample we're going to give it the standard resistivity matrix that we all know and love. So we're going to say pxx divided by pxx squared plus pxy squared So now we have the bulk set up with the normal resistivities, but now we have to do the surface. So in materials we're going to add a layered material. We only need one layer, so we're just going to add a single layered material to make our life easy. And now we need to select all of the boundaries of the conducting bulk. And I mean all of them. So it's easiest to select the under here first, the part that connects the contact to the sample. So to select under it, we're just going to put our mouse over, and we're going to move the scroll wheel up, and that will let us select what is below. We're going to do the same thing here. Scroll wheel up, 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 and then we're going to select the top surface, the sides, and I believe that is all of them. So we've selected the surface. Now we are going to give it a relative permittivity of 1 and electrical conductivity of 1. We're not going to set up the conductivity matrix quite yet. So now, and we're going to give it a thickness that's very small, like let's say a nanometer thick. And I'm going to call this the surface. And I'm going to hit save. Okay, so the first, so the next thing we have to do is we need to give it the surface XX and XY. Now, unfortunately, in COMSOL, we can't give it like actual surface values because the dimensionality is all wrong. The resistivities, you know, they're just ohms for the 2D case, but COMSOL doesn't do that. They do 3D. That's why we define the surface down here, or the thickness down here. So we know what the thickness is. So all we have to do is convert U into the 3D resistivities. I'm going to make a new set of parameters so I don't confuse myself. And I'm going to call these the 3D resistivities. And if spelling mattered, it sure would. So now I'm going to just do PSXX3D. This is going to be the 3D surface XX resistivity. And this is going to be equal to the surface resistivity divided by the thickness. Let me remember what that is. Yeah, it was 1 nanometer. So I multiply times the thickness. That is roughly the 3D resistivity. Same thing with PSXY 3D. So these are what will be going inside the conductivity matrix. So let's do it. Open up the full matrix. I'm going to say U divided by U squared plus boom, there we go. So now we have the surface conductivity set up as well. And now we're going to go back to electric currents and shells. We're going to set the shell type to a layered shell. We're going to restrict it only to the layered boundaries. So right now, only the boundaries that have the layer property that we defined in the material will count. And I think we're A-OK. So we're going to move on to multiphysics. This is one of the cool things about COMSOL is you can have a lot of physics done at the same time. So the last big thing that we have to do is in multiphysics we have to right click and we have to give it the electric current solid physics property. So I'm going to select all boundaries, and what this will do is it will give the volume transport, and it will calculate that via electric currents, and the shell transport will be calculated by the current in shells. And remember, we need this. We need this for it to work. Then I'm going to hit save. And next I will move on to the meshing. I set the meshing to be extremely fine because I'm a psychopath. Let's see if extra fine works. It works, but can we get coarser? Coarser. Okay, this will be good for demonstration purposes. Okay, so last thing, I go to the study. This is when I have to define all my parameters now. So I need to define xx, xy, surface xx, and surface xy. Remember that the 3D ones are downstream of the surface. So how I normally do it is I will give some sheet resistance of some value, such as like 1 kiloohm, and then I'll vary the XX, and what that'll do is it'll give us the parallel resistance model that you've probably seen in like every circuit textbook. So I'm going to vary U over a logarithmic sweep. Let's real quick back in the envelope calculate what the sheet resistivity is going to be. So the sheet resistance is resistivity times distance traveled divided by width. So the distance traveled between these 2 points. So the width is about 1,400, I believe. So that would be 1,000 resistivity divided by 1.4, let's say 1.5 e to the minus 3 comes out to massive number. Did I get the width right? Oh yeah, I got the width way wrong. So the width is 1,100 microns. Yeah, so it comes out to be about a mega ohm over that distance, if we've done this right. Though I guess there's no guarantee that we have. So we expect the sheet resistance between these 2 points to be about a mega ohm when the resistivity, the bulk resistivity is high, and a lot less when it's low. I guess then I gotta multiply by the distance between them. Hold on, let's do this right. Let's do it right. So 0.43 e to the minus 6. Okay, so it comes out to about 1,000 ohms. So when the bulk resistivity is very high, the back of the envelope calculation gives a sheet resistance of about 1,000 ohms between these two. Alright? So, but that's just when you are very high. When you're very low, this guy will take over. So, let's do it. Logarithmic. That's when this guy is dominant, and it is not dominant at 1 e to the 6. We can do one step a decade. And compute. While that's going, I will work on the MATLAB code for Dimitri. No, there's a problem? Oh, dang it. Specified combinations? I want all combinations. I'm an a la carte type guy, you know what I mean? I don't mean anything by it. Luckily, this is getting edited out. So I'm going to change folders. What, are you done already? So the error I just got was the residual is too big. How COMSOL does it is it will converge on a solution, but if the convergent factor is too large, then it'll throw an error. The two ways to fix this are we could make the tolerance bigger, meaning it's less accurate. We could change linear to nonlinear, which occasionally will give better results. Or in mesh, we can give it a finer mesh. I'm going to give it a finer mesh. I'll go extra fine. Ooh. Let's see if this fixes it. Back to MATLAB. Well, it seems to be working so far. Okay, so the data is equal to, well, first, I did hit an error. Oh my gosh, I'm a silly Billy. Did I? Oh no, I did. I did. I'm not a silly Billy. I'm a serious Billy. Multiphysics, current shells. Did I miss something? I do not know. Well, another way to fix it. User-controlled mesh. I will tell it how small to be. God, the regions right here always have the biggest problem because they're the boundaries, but they also matter the least. No! Okay, let's move the boundary. The ground. Let's move ground. Ground, more like shpound. Mesh. Okay, we're gonna make you super smooth. Super friggin' smooth. Nothing changed. We'll see if nothing changed. I'm gonna change you back to linear. I wish I could give it an initial. I have an idea. Because we know that the voltage between these two is roughly going to be 800 ohms. So if I could just say that, it would make this so much easier. Because it could start at that 800 and work out. The alternative is I just do one where the bulk is very conductive, just to see if my sim results get us that. If this doesn't work, that's what I'm going to do. Speak of the devil. Did I not? No, you've... So this isn't terminating, or it's not even conducting at that. Oh, I missed a spot. No, I didn't miss a spot. It's right there. So that's just gonna happen regardless, huh? There we go. It all worked out. So, now we're going to go to derive value. We've got V1 right here, but we want more. I also want V2. And V3. And they're all going to feed into a new table called bulk sweep. Anywho, so let's evaluate. Wait, no. Okay, so we do get the value that we expect. At least the same order of magnitude, and that's good enough for us. I guess that kind of makes sense because it also conducts on the bottom as well as the top, so it would cut the resistance in half. So I would say we have a success, meaning we can continue on with the sweep. So now we're going to sweep this value from this guy to this guy, 1 step per decade. Then we're going to hit the compute button and watch the magic happen. This will take a while, so I am going to go and this is my screen. Awesome, it's done. It is done. Now we have this for basically all of the resistivities. Yeah, I think we're good. So now what we are going to do is throw it all into the big table. That's the lovely table that we like to see. And now we are going to jump into MATLAB and plot it. So I already did some of this on screen. I'm sure you saw in the fast forward part. But yeah, now I've got R12 and a bunch of other goodies. I'm going to plot TXX and I'm going to do R12. Set, get current axis. X scale log. I think that's how it works. Oh yeah, I was right. So now I'm just gonna set Y scale as log as well. And boom. That is what we want to see. So this is the bulk dominating part, and eventually when the bulk gets too resistive, the surface dominating regime takes over and it saturates at the like 500 ohm part that we found. So technically we kind of have all the bulk stuff we need. Like, if we wanted to be really mean, we could just make Dimitri figure it all out from here. Because if he knows what the sheet resistivity is, 1 kiloohm I think I said it as, then he can just take this slope to get the geometric factor, and the ratio between 478 divided for 1 sheet resistance to get his thing. But I'm going to be a little nicer than that because I'm a good person. So I am going to find the slope myself, and I'll find the ratio myself as well and give it to Dimitri. But that is how we do the bulk and surface conducting for the longitudinal resistance.